Our project is Material and Structural Response under Dynamic Loading, a joint project between Material Science and Engineering and Mechanical Engineering. Our group members, on the left we have our mechanical engineers, Pujan and Stephanie, and on the right, our materials engineers, Nicholas, Brianna, and Alexander. A basic overview of our project: we are simulating high strain rate events in turbine engines. These events cause the structural components to experience a rotational imbalance, creating a very large force and hence the high strain rate. We are varying strain rates in tensile tests from very low to very high, and we are producing stress strain curves with the goal of increasing the mechanical properties of aluminum alloys characteristic of those used in turbine engines.
Now, historically, fan blades have been designed assuming that they are exposed to very low strain rate loading. In real life, they're actually exposed to very high strain rate loading, which when this happens, they're actually stronger. What this basically means is that if it's thinner, that it could still have the same strength at a high strain rate than at a low strain rate. So basically, fan blades could actually be lighter because they're thinner, and this will make the plane lighter overall.
So for this project, we are tensile testing aluminum alloys to be able to create a relationship between the increasing of strain rates and the material properties. So the aluminum alloys that we are looking at are aluminum 6061T6, which is pictured on the right, aluminum 3003H14, which is pictured on the left, and aluminum 7075T6, which is not pictured. We are testing these at strain rates of 0.01 Hertz, which is a static test, and therefore it should reaffirm the values of the material properties that are found online. And then we are testing at 50 Hertz and 100 Hertz. 100 Hertz is closer to that of the rotational speed found in an engine turbine, and 50 Hertz is being used as a middle value in order to help us create the relationship that is seen at these higher strain rates versus these static rates. As mentioned previously, we're doing these different tests at different strain rates. So here is a 50 Hertz test of aluminum 3003H14. So on the left is a picture of the test happening, and on the right is the load versus displacement graph that was given via the machine. So we got a little bit of a higher strength value than what is reported for the low strain rate tests, basically the static tests, and we did see an increase in brittleness in these tests.
Within the ANSYS software, we modeled the aluminum 6061 T6 specimen using a static analysis. We applied a variant displacement in order to simulate the testing that is done in the lab. From the simulation, we found the stress and strain in the direction of the pull. We used this simulation to verify our lab testing data of the material load and displacement recorded by the admit machine.
For the analytical part of the project, we used the LS-DYNA model to simulate the test. We used the Plastic Kinematic Model 3 from the LS-DYNA manual to roughly simulate the stress and strain curve and see the extent of failure within the structure. We first created a Google spreadsheet with the admit data at different strain rates, and then used the Cowper segment strain rate model equation to get similar yield stress values using C and P constants. From there, we would then use the C and P constants along with other material properties such as the Poisson's ratio, the density, the yield stress, and the elastic modulus, and plug those values into the model and run the simulation. Here we have recorded the simulation of the material model 3, and in the model, the specimen is being pulled until it fractures, similar to what would happen in the admit machine. On the right is the stress versus strain diagram created from the model in the LS-DYNA program. This would be then compared to the graphs created from the admin machine to see whether the results are correct or not.
We also did some additional analysis within LS-DYNA. We created a simple supported beam model to test the specimen at different velocities. This allowed us to determine the percent deformation of the beam at different rates. Using this simulation, we can determine the extent of failure through the yield and fracture of each case.